Hi class, welcome to our next section, chapter 12.3. We're going to talk about geometric sequences, and this is going to be the last type of sequence that we discuss. And in the following sections, we'll just talk about the uses of sequences and some of the cool things that we can do with those. So a geometric sequence has the form of starting with a constant a, and then each time we progress, each value is multiplied by a value r, a constant value. So in the last section, 12.2, each new term was had a difference of a constant value. Each time adding 2 or each time minusing 3 or something like that, right? Here, each time we're going to bump up in value by a multiple of r, right? So maybe we start with 3. And the next one we multiply times 2. So we get 6. And the next one we multiply that times 2. So now we have 12. And then times 2 again. So now we have 24. And then times 2 again. You know what I mean? So geometric sequences are a little bit different in that you grow a lot faster than in an arithmetic sequence where you're adding a constant each time, right? So here you're multiplying by a value each time. So as an example, let's consider the geometric sequence 3, 2, 4/3, 8/9, etc., etc. So if I want to figure out what my sequence is, a is always easy to find if I'm given my terms. It's the value 3. If I want to find r, well, I know that the difference between the first term and the second one is that I'm multiplying it times r. So I figure to myself, what times 3 gives me 2, right? And then once I figure that out, then I have my sequence. If I want to know, I can really just set that up as an equation, right? 3 or 2 times, I don't know, let's say r, right? 2 times r equals 3, solve for r, and that's how we figure this out. Notice here, if we just go back one step, my index for my general term is n minus 1, and that's because here on my first term, that would be r 1 minus 1, or r to the 0, which is why it's just times 1, just my value. So my index here, I need to have n minus 1. Okay. So here I know that my a is 3 for this sequence. To find r, we just use the next term. Really, we can use any 2 consecutive terms, but it's easier to use this. So I know that 3 times r will be my second value, right? So 3 times r is whatever the second value is. So r is 2/3. So in order to get from one value to the next, I just keep multiplying the previous value by the value 2/3. So my general term here is 3 times 2/3 to the n minus 1 power. That's the general term. Now we can add these things together and get our nth partial sum, as we've been seeing in each section. Sums of the terms of my sequence is a very important thing. So the nth partial term is just me adding up all of my terms until the nth one, right? In order to find the generalized formula for this nth partial sum, we're going to take our partial sum and we're going to multiply it times r, right? It's just a little trick that we're going to do in order to formulate our answer. So I'm going to take all these terms and I'm just going to multiply it times r, right? Because my partial sum, which is this thing, if I multiply it by r, I do that on both sides, so everything bumps up by one value. So a is now a times r, a squared is now a cubed, right? A r to the n minus 1 is now a r to the n. Everything has been bumped up by one value of r, one power of r. So what I'm going to do is I'm going to subtract these two things. Okay, so Sn minus r Sn means I'm going to take this and I will subtract this value. I'll also do it term by term. But it'll be easier just do it one at a time. So I will have from a to arn minus 1 minus each of these. So all these signs are going to turn negative. So I have ar squared, all the way to arn. So if you notice, there's a lot of doubles. This is positive, this is negative. That'll cancel. Ar squared, negative ar squared. Arn minus 1 minus arn minus 1. So what we're going to be left with is that and the nth partial sum minus r times the nth partial sum is just a minus arn. Okay, So now what I can do is I can pull out this common term of S sub n, the nth partial sum. Okay, pull that out, and I have 1 minus r here, and here I can actually pull out the common term of a. So now when I try to isolate the nth partial term, I have a times my starting value, my first term in the sequence, times 1 minus r to the n divided by 1 minus r. So that is my nth partial sum of the geometric sequence. So let's do an example. Let's find the sum of the first 10 terms of this geometric sequence. So the nice thing is that we've already used this. I know that a is 3, and I know that my r, that's all I need, is a and r, and however many terms I'm trying to find, right? So I know r is 2/3 because we already did the work for that. I'm trying to find the first 10 terms, so I just plug everything in. First term times 1 minus r to the 10th over 1 minus r. Okay. So here, this is 2 to the 10th, 3 to the 10th, instead of actually just plugging it in and trying to find the value. There's a lot of fractions here. Actually, you probably can, because this should be a whole number, because we're adding whole numbers. Well, you'll actually get a fraction, right? So I'm adding a bunch of fractions together. So in order to keep things exact, I'll do some algebra, right? So this is 2 to the 10th over 3 to the 10th. That means 1 can turn into 3/10 over 3/10. So this is my common term. I have 1 over 3 here, which means when I multiply by the reciprocal, that this actually turns into 3/9, because this turns into a numerator, so I can cancel that. I also have another 3 here, so then this turns into 3 to the 8th, right? And now I can plug this into the calculator. I have an exact value for my numerator and an exact value for my denominator. So I have 58025 over 6561. If you give me a decimal value here, that's not in line with what we're doing here, right? So make sure you give me an exact value if we're asking for a sum for a geometric sequence. Okay. Now let's talk about infinite series. So far we've only been talking about adding up into the 100th term, the 10th term, whatever term. What about the sum if we let it go on forever? Now you might be saying to yourself, well, no shit, Professor Williams, if I let the sum go on forever, I just keep on adding more and more values to it, right? Like if they're all positive, for instance, shouldn't it just go to infinity? Or what if I'm just continually subtracting things, right? Then shouldn't it go to negative infinity? It's not always the case, okay? So again, you would think that if we just add a bunch of terms together forever and ever and ever and ever, that we would go to infinity, right? But that's not true. Consider the sequence 1, 1/2, 1 over 4, 1 over 8, etc., to 1 over 2 to the n minus 1, right? So when we have 1 here, we have 2 to the 0 power, so that's 1 over 1. Okay, so this is our sequence. So each time I'm multiplying by 1/2, right? So r is 1/2 in this case, and my a value is 1. So the sum of these values, starting from 1 up to infinity, can be represented with squares. So we'll start off with a square of area 1, then a square of area 1/2, and then so forth and so forth. So we have the unit square, 1 by 1. We're going to add to this a rectangle with a base of 1 and a height of 1/2, so it has an area of 1/2, so that's 1.5 so far. Then we add one with an area of 1/4, so it should be half of this amount. Okay. So we have 1/4 and 1/4. And then, so we have 1/4 on this side. So let's go height of half of this, which is 1/8. Then here we'll have 1/8 by 1/8, so 1/16, and so forth, right? So half of this and half of that. 132, 164, 128, so forth and so forth. So if you notice, I keep getting smaller and smaller and smaller, but I'll never actually fill this out. Okay, it'll just get microscopic. I can zoom in forever and ever and ever, and it'll never fill out the rest of the square. But as you can see, as I get closer and closer to very, very small amounts, I get very close to finishing out one more unit square. So the sum of this is going to be 1 plus 1 as my sums go to infinity. Okay, so it's very clear that the sum of this sequence is going to be 2. Right? We say that it converges. If a series converges to a single value, like this one does to the value 2, it's a convergent series. If it does not converge and it goes to, like we thought it would, infinity, we call it divergent. Okay, so it's either convergent or divergent in nature. Right? So if it goes to either positive infinity or negative infinity, then it diverges. There's one more option, but we're not really going to talk about it now. We can leave that for a Calculus 2 course. But we can also say that it alternates in sum, and it oscillates about a certain number. It doesn't converge or diverge. It just doesn't do anything in that case. Okay. So sum of an infinite series. If r is less than 1, which we have here, our r was 1/2 actually, right? If r is less than 1, then the geometric series represented by this thing, right? So different values of k, is going to converge to the sum s equals a over 1 minus r. So in our case, we start with 1 divided by 1 minus 1/2 was our r. So 1 over 1/2 is 2. So that's a quick check. If our value of r is 1 or larger, we're going to blow up to infinity or to negative infinity, depending on if our a is negative or not.